Air India AI-171 causality. Boeing 787 loss of thrust and resulting crash on takeoff. Ahmedabad, India, 12th of July. In memory of Captain Samit Sabawal, First Officer Clive Kunda, all passengers, crew, and ground casualties. So for those of you who don't know me, there's a reason you don't know me. I'm a no one. I do have a little bit of a background in aviation, but not as an aircraft engineer. But that does not mean that I have no place to talk about this. Back in the day, I completed most technical subjects for the Australian commercial helicopter license. I got a perfect score, well, 95%. One question wrong in aircraft general knowledge, AGK. The question was about overread or underread on descent with a vertical speed indicator or something like that. I can't remember what I got wrong. It was something to do with that. Everything else was good. I got pretty good scores with aerodynamics and navigation, and absolutely atrocious, and the reason I stopped continuing, with air law and meteorology. Incredibly boring subjects. I'm not interested in clouds. Didn't pique my interest. And air law was just absolutely ridiculous. Not interested. I decided not to fly anymore. Had a fight with the boss, quit the job, and then transitioned, pardon the pun, into telecommunications overseas. I used to research. I used to be a research analyst for a mineral deposit assessment and databasing company, doing basically QC, quality control, on data input and making custom reports on mineral deposits, mining, processing technologies, mergers and acquisitions, separating lies, spruiking from reality, by learning about the topics that I was dealing with and becoming an expert in each one of them. So that was my history and research. Now I'm working in telecommunications, responsible for things which are similar to the issue at hand here. I do a lot of work with uninterruptible power supplies, particularly AC, but also DC, for my company and also for our customers, some of which are large international telcos that you would know of. They constantly ask for my work. They want me, these other customers, they want me to keep building these things for them, because I seem to be pretty good at it. I've got practical knowledge in electrical circuits and electronics, and I'm not a novice. Now, although I'm not formally qualified in aviation, that doesn't mean that I don't know what I'm talking about. Okay, I bring real world insight and experience with electronics. Now, no disrespect to pilots, but pilots do not know what I know, and even some maintenance aircraft engineers know enough, but not enough to know what I know. Yeah, I said that. Look, you might be very confident in what you know, but never think that you know the full truth. Okay, now I don't even do that, but I think I've worked it out. Okay, why am I doing this? Within 2 hours of the plane crash, me and my dad were watching, glued to it, and I was upset. I needed to know what happened because I frequently fly, not frequently, but relatively frequently fly on the 787. I mean, it felt risky. I just wanted to know what happened, because now that means an aircraft that I'm commonly flying on is no longer, feasible in my mind. I just suddenly felt at risk. Ever going on it again. Now, I've got no desire to make money. That's why there's no ads in this, and it's also why this video is not promoted. You probably won't even see it, unfortunately. So I don't want to make any friends, but I don't want to make any enemies. So please don't be an asshole. On that note, so just take note that these videos are not for entertainment. I'm not a YouTuber. If you don't like the video, feel free to ignore it. Leave it for viewing by the educated or inquisitive population without leaving your arrogant mark in the comments. Okay, just you can go through this in your own time. Just tried to record this video 15 times now, and it keeps taking too long. So just pause that and read all of that and learn it. That'll bring you up to scratch with the basic terminology I'm using in this video. Okay, how did I get to an electrical analysis? Originally, I was suspicious of things, but then when one of my bosses, Tom, thanks Tomo, pointed out a video on X from the passenger on the previous flight talking about things not working. I had not seen that it wasn't working well also whilst in the air. I wrote that off as an APU failure. When he my boss Tomo sent me this. Thanks, mate, because that was a critical piece in the puzzle. The fact that it wasn't working whilst flying, that's the clouds out there, okay? That proved that it wasn't an APU failure. The aircraft was broken whilst in the air and on the ground, and no one said anything in that flight before. Okay, so look, I know electricity, so I'm going to look into this. I kept reading about battery failures and 2013 grounding, and I just suddenly thought, well, hang on a minute, this all sounds like battery stuff. Like, what if it's that again? And then, look, when we saw the recorded interview of Vishwash Ramesh, good on you, mate. I'm glad you're alive, and I hope you can get back to, a somewhat semi-normal life after this horrible incident that you went through. I'm really sorry. Look, what you said in the hospital bed is enough of a clue to set someone off looking at the right things. So look, he mentioned that there was a noise. He didn't say a bang, he said a noise, a direct translation. Then the aircraft felt like it hung in the air. The green and white lights turned on. That's the Wells lights. That's important. The wireless emergency lighting. And that the aircraft tried to go up, he said, but that just it didn't go up. It just accelerated with more speed into the building. Okay, Vishwash, if you ever get the chance to comment on this, mate, I'll be so happy. If you can tell me that's what you meant, thank you. If not, correct me in the comments, mate. You're welcome here. All right, lithium battery problems. Why am I focusing on that? Because they were never fixed. Okay, so after the 2013 problems, there was a guide put out. I couldn't believe this. They were talking about, this like it was like a ground-based structure. They weren't talking about it like it was an aircraft. If there's a fire on the aircraft, we have a problem here. You don't tell people how to put up flames on the ground. This is not a building. It's an aircraft, a passenger-carrying aircraft. All right. Look, I've found lots of aviation, incident databases and studied them all and tried to work out what's actually, how likely is it to be these batteries. And after doing so, I'm more convinced. Okay. I then discovered that the two batteries that are talked about are not redundant batteries. There's one at the front for the left and right, and then one at the rear to start the APU only and to do a couple of other things like power the lights. Okay, there's only one battery that can actually help with powering the critical instruments, and that's the front battery. Okay, and it is sort of isolated from the rest of the bus by a relay, which is a switch, and a diode. The switch above the pilot's head turns on and off a battery relay, and I'll get into the intricacies of that later. The diode, it's pretty much always connected during flight. The diode makes the battery act like a DC online UPS. That's what the diode's for. Okay, so I noticed that there was a couple of ram air turbine deployment incidents recently, including this one that we're seeing now, the AI-171. In January last year, Virgin Atlantic, this was a quote from someone on Av Herald who said, my son was on this flight. He was, he said there was a loud bang followed by a whooshing sound. I suspect that what he heard was a deployment operation of he means ram air turbine. The cabin lights went off and the emergency lights came on. Where have we heard that before? The pilot said they had a generator failure and were returning to Heathrow. Now, the pilot would say generator failure without knowing what's actually happened. Okay, but if there was a generator failure in the aircraft, engines had failed, well, we'd be talking about a crash here. This plane didn't crash. Okay, so it wasn't a dual engine failure, was it? He would have said the engines failed. He said a generator failure. Okay, so I suspect, and I put it to you, that all of these incidents, including the one just last month, that LATAM landing back at LAX with the rat deployed, I put it to you that these are all experiencing DC bus anomalies. And when that happens, when there's something going wrong with a DC bus and both of the buses turn off, you get loss of all electrical power going from the rectifier units, the transformer rectifier units, to the captains and first officers' flight instruments. Bam. That's one of the reasons that the rat will deploy. And that, I'm telling you now, is the reason that the rat deployed in all these three. The engines did not fail. Another way that it can is if the engines have failed. Okay, but what I will show you later is that the way it will deploy if the engines have failed is because the engine's power output through the variable frequency starter generators, just the generator part, goes below output and goes offline. Okay, I'll explain that to you later. Yes, it's manually deployable, but if you're going to commit suicide, you don't, turn the engines off and then push the rat for good measure. Okay, sorry, you don't. So you can write that one off even with your ridiculous comments that it's suicide. Okay. One of the pieces of evidence that the rat deployed first and that the engines didn't cause the rat to deploy. This is just one. I will make a few points of this during the presentation. Okay, the time it takes for the engines to spool down from takeoff to below the minimum threshold required to make power. Okay, there's 360 hertz up to about, I think it's 360 up to 800 hertz. Okay, 400 is wrong. It's 360 hertz. Okay, and that speed there is talking about the input speed, and that doesn't actually necessarily one-for-one relate to the N2 value. There's a 1.3 gear reduction. Nonetheless, with all of the maths in, it would take an awfully long time, and before I learnt too much about it, my maths said it would take a minimum of 5 up to about 8 seconds from cutting off at takeoff thrust or full thrust, okay, for the VFSGs to go below their online status to offline. So it would take about, I thought, 8 seconds for the rat to deploy after engines started to spool down. It actually turns out to be worse than that. It takes a lot longer than that. We'll get to that later. This also concurs with the fact that the ADS-B, sorry, that's not D, ADS-B data stopped at the end of the runway. I'll explain that as well. The VFSGs can provide enough power to power these systems to just below idle. Okay, but it load shed the transponder and all of that stuff first, all of the non-critical stuff first, which is why the ADS-B for Bravo data stopped, not D. Now, there was a flight last year, which I'm a little suspicious of. This bloke here was a passenger. Here's the lady on CNN interviewing him. And this is I couldn't post the video here, so I'm just going to tell you what the caption's saying, what he said. He said that the pilot said the gauges went blank, didn't have the ability to fly it. Okay, now this was talked about as a sudden descent, and then it was given some causality that the pilot's chair moved because someone who was delivering food pushed the chair moving switch. I just call bullshit. So what actually happened here? This guy said that the pilot, he immediately engaged with the pilot as he came out the back, and he said, "What was that?" And the pilot openly admitted. He said he lost control of the plane and his gauges just kind of went blank on me. That's what the pilot said to this guy. He said that for a brief moment he couldn't control anything, and that's when the plane did what it did. Okay, this doesn't sound like it hit turbulence. That sounds like something went wrong. And then the plane re-engaged, and we had no issues before that and no issues afterward. Okay, their engines didn't fail. Something went wrong with that airplane, and I put it to you that it's exactly the same here, and it's being sort of covered up. Because it was a worrying moment for the 787. Unfortunately, it happened again, and it happened on takeoff this time. All right, and it happened with a very bad result to some of the fuel control, not switches, the fuel control relays. Okay, now that same flight we're just talking about then, around 2 hours into the flight, it dropped suddenly, losing over 300 feet. Now, that doesn't mean you just went bam and hit turbulence. You don't lose 300 feet in turbulence. That's a descent. That's a big, fast descent. And so what I think happened here was something went wrong with the DC buses, and it possibly cut the engines as well, and they restarted. Okay? And all we hear about is what the media were able to report from this, which was what was allowed to be leaked. Now, this guy on AvHerald, this isn't me, please. Okay, this is just some awesome guy on AvHerald, Aviation Herald, who said that he found it like a cover-up for an electrical problem. Thanks, mate. I agree. Read that. I agree. Moving on. Okay, lithium battery history. Everyone keeps telling me that they fixed the battery. No, they didn't. It continued to fail, and here's why. So you had the 2 incidents first, APU battery, then the main battery, then it was grounded for months, and then it just happened again. Okay, in 2014 it happened again. So don't tell me that it was fixed. It wasn't fixed. And look at that. United Airlines, Paris, Charles de Gaulle, lithium battery. They had a single cell. There wasn't a massive fire or anything, but the battery failed. It just keeps happening. And there's a reason why it keeps happening. There's a single point of failure which they didn't know about. Now, back in 2014, people were saying, this doesn't make sense. The battery shouldn't just fail. The suggestion is that the fault may not be in the battery, but in the battery protection circuitry. That could include the diode, the battery management unit, the contactors, the charger, anything. But I'm telling you, it's the diode. More experts weighing in, agreeing with that. They never actually got to the root cause. They successfully contained it. they're just repairing it. You're not actually fixing the problem. Okay. Also, the French, after the 2014 incident, this is an excerpt from the end of the Japanese Transport Safety Bureau. The French were saying, yeah, we recommend continue studies of the internal short mechanism and consider the effects of that, okay, on operational conditions, such as aircraft, electrical environment, and the risk associated potential transient current and voltages. That's what I'm talking about, transients. Continue studies on the impact of humidity, heat and vibrations. Remember, this battery is mounted right near the nose gear, and the nose gear slams into the runway lights, the center lights, as it goes down the runway. If it's sat in the front of the plane, you feel the doosh, 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 doosh. It's not an accident. That's what the pilots are trained to do. Hit as many of those lights as possible, and then you're on the center line. All right? Improve the lithium-ion battery's quality and reliability. They should have also said quantity, if you ask me. There should have been more with better isolation. Now, these are my suspected similar events. You can read that and go and investigate them, but I actually have a suspicion that all of these are recent incidents of battery failures, especially the smoke in the cockpits. I haven't got any proof of these things, but you can do the research and you can't find anything to suggest what the actual root cause of this is. Okay, I suspect that all of these, including the recent one, were all dual DC bus failures from the same problem, but they were in flight. Now, why in 2024 would there be a deal with an Indian company for a very particular battery protection part, the battery diode module? Why? Why in 2024? Why would you suddenly change from Thales, the big French company that was making it before? Why would it suddenly change? So I asked ChatGPT. This is the only ChatGPT or any AI I've used in this entire thing. I used it as a search tool. Okay, I do not learn anything from that other than using it for searching for finding documents. Okay, I asked it to show me what are the similar deals where they're making electrical parts or machine parts when they weren't already making it. There's only these ones. So it's this battery diode module is a very specific thing, and look, that infers to me that there was a problem serious enough with the original one that Boeing was seeking a redesign and resource from a less conspicuous supplier without too much media attention. That's what the battery diode module looks like. Okay, major French company was making it before. It's inside the most failure-prone system known, and they don't want anyone to ask questions. And I think that they were upset when Scient DLM made this announcement because we didn't see another announcement after it. I think they were told to keep quiet, and they had like a non-disclosure agreement, and they never spoke of it again. Okay, this is what the battery diode looks like. The module, you can see two diodes in there. Well, it's probably more than that, but it proves that it's not just a diode. Okay, it's a module. You've got an input and output, and then a little output for powering. I think it's a small wire. I've seen it, but I think it's actually going to the battery relay switch as the source of power for the main battery relay. I think it comes through that, so that we're not getting direct power into the aircraft without the diode. Excuse me. So here we can see a heatsink. Notice that it's not actually like enclosed. It needs airflow, but notice the airflow is not that encouraged. This doesn't have any fans in it. It's just a heatsink. And to me, that's not good enough. If it's a diode, it should be looked after. Diodes fail when they overheat. We'll get into that. So what does a diode do? What does it do? How does it do it, and why? Diode lets electrical current flow in only one direction, particularly DC current, okay? And it's used often in DC uninterruptible power supply and DC battery systems for isolation, which like it's used here, and for rectifiers of alternating current to direct current. Now, a lot of solar guys would know of Victron. I love Victron, except their horrible operating system stuff. But look, they make some good good affordable battery isolation gear and diodes and stuff. So anyone who's familiar with it will know that they're built around a heatsink because heat is the killer of a diode. Okay, if it's operating in a hot environment, as in too hot, it will absolutely shorten the life of the diode. A diode's reverse leakage current increases exponentially with temperature going up. Okay, and then you can look at this. It goes up, it gets worse, it behaves worse, and then it turns into its own type of thermal runaway, similar to lithium battery thermal runaway, where the higher leakage current means more heat, which means more leakage, more heat, and so on, and it just keeps repeating until it basically destroys itself and becomes a short circuit. That's what's happening here, and I think that's why they're asking for a new battery diode module, probably one with a fan or with a better heat sink or just something that can be tested. Because in this case, if your diode fails, the battery is exposed to all kinds of problems, and you can't do that if people's lives depend on it. Okay, so how does a diode fail? The most common failure for a higher current diode, provided that it wasn't exposed to ridiculous current, okay, is diffuse short circuit, diffuse short. Okay, if it was massive current blowing it up, it would explode and open. This is not massive high current. This is transients, and just it's a relatively high current diode which failed. Typically, a diode fails as a closed circuit. There you go. Due to overvoltage. Now, that doesn't necessarily mean, you know, ridiculous overvoltage, but just constantly overvoltage and voltage pulses. Things that are so bad, like electronic static discharge. Okay. NASA had problems using diodes for an interplanetary propulsion system. You can read that if you want. Their diode failed and they made a big report about it. Go and Google that. And they gave up on it. Okay, so why is there a diode in the 787? It's simple. It's to allow critical systems to continue to function during power transfers. And that means anything where the DC stops being DC, something's got to keep it going. And we do that with, like, you know, a no-break UPS style battery with a diode. So regardless of what any of my trolling commenters tell you, I can assure you that this aircraft's DC system acts like an online dual conversion UPS all the time it's in the air. Okay, the battery bus is connected to the captain's bus anytime the aircraft switch is on, provided that it's not on the ground with a power cart supplying power. As soon as that power cart is gone, okay, I can tell you because I've looked at the ESIC live display on the multifunction display. When it's in the air, there's a green thing showing the battery relay connected in flight. Okay, you don't believe me? Go look. All right. If the aircraft is on the ground, however, I think I've made a mistake with this, by the way, this sentence here. If the aircraft's on the ground and the battery switch is on, the moment a power cart starts supplying external power, or the APU supplying power, the battery relay would open, and therefore it wouldn't need the diode. Okay, so sorry, I made a bit of an error there. But otherwise, the battery relay is closed and then relies on the diode to protect it. Why? Because that's the only way that a critical DC-powered system can stay online in the unlikely event of a power failure of both critical DC buses. These ones here, captain and first officer. Captain sits on the left, first officer sits on the right. Okay, that's the beauty of diodes and the reason a diode exists on this aircraft. Okay, so that it doesn't have to wait for a switching event. It doesn't want to wait for this switch to turn on because the captain instrument bus can't turn off. We want it on all the time. So this is like a no-break UPS. Sorry, that's how it works. You would read in some articles about something that makes it look like it only happens on the ground. No, you've interpreted it wrong. I can go through a document that shows it, but I'm not going to spend the time. I don't need to. Okay, sorry, but anyone who says that this is open during flight is wrong. So here's what he misinterpreted, or partly what he misinterpreted. I've seen his sending me messages on other platforms, still completely wrong. When this switch is on, the battery switch above the pilot, okay, that there, when the airplane is on the ground, so if the airplane's on the ground, okay, and the power cart is not connected, then it closes the main battery relay, okay? Then from there, the battery's powering the captain instrument bus and first officer instrument bus. Okay, that doesn't say that once it takes off or leaves the ground that opens. It doesn't do that. It's just talking about when it's on the ground. Okay, if the ground cart was there, that battery relay would open. Okay, because it's trying to charge the battery critically, and they don't want to use the battery. It wants to use the ground cart, okay, to power the TRU, the transformer rectifier units, to charge the battery. They don't want to use the battery. Okay, now, still looking at the diode here, you can read that. In this way, the backup bus supplies power to the central TRUs. This is about the backup power from the ram air turbine, how it works. So the ram air turbine would normally, when it's deployed, would go through the backup bus and would powers this one and that one, and then isolates the rest of the AC bus so that it's only powering these inner transformer rectifier units. Okay. So what happens to a lithium battery after its isolation diode fails? It's simple. It destroys the battery. Lithium chemistry batteries require a very special charge profile. Yes, it is very special. I can't plug any old lithium battery into any of my UPS systems. I need a particular charger, or I need to make sure that the UPS system I've got is capable of charging lithium. Okay, it's a very carefully monitored battery management system. In this case, it's called a BMU, battery management unit. The only way cells can be protected is by monitoring their voltage. There's no other way to do it. This means there's all these different leads which monitor individual cells on this battery pack. Okay, this does leave minor cell issues hidden and invisible to the main battery management system. Little things, it just can't see everything. So look, if the battery management system doesn't see little transients, okay, if these little things are just happening, within 31 volts and, just transients, just spikes, okay, the battery management unit can't fix that. Okay, as long as it's roughly sitting around 31 volts, it'll all be fine. If it gets over that, then the contactor would open. This didn't get over. It's not being overcharged. It's being held at charge. If you keep a lithium battery at its normal charge, I shouldn't say float, if you keep it at its normal charge in a very short summary, you're basically going to destroy it. It'll cause dangerous failure. Degradation, swelling, capacity loss. Okay. Why? Because holding a lithium ion cell at maximum voltage keeps it under continuous stress, driving side reactions, copper deposition, electrolyte breakdown, and that permanently reduces capacity and reduces the risk of swelling and thermal runaway. Okay, now this is why when you buy a laptop or something, you don't get it, they don't hand it to you in full voltage. You get it about 50 to 70% state of charge. Now, you don't leave lithium chemistries at 100%. You can charge it as long as you end up using it. So this is what happens when the battery failed on the Takamatsu incident landing. This is the main battery that broke before the grounding, not the APU one. This is the main one. So once it failed, this is what happened. All went nasty. All right. Now the Japanese were so close to joining the dots. Unfortunately, even in this document, in the JTSB 2014 report from the Japanese Transport Safety, sorry, that should be JTSB. They mentioned the failure within the sentence, within one sentence of talking about the BMU, the battery management system. They then mentioned the BDM, but they didn't connect the dots and realize that the failure of that is the reason that the battery was getting charged wrong. Okay? If the charger stops charging as instructed by the BMU because something's wrong, but the diode keeps charging, then that's all pointless. The battery diode is a form of battery protection. Okay? And it has failed, meaning that the BMU can't protect it well enough. It would have to be preemptively stopping every transit. No mechanical contactor can work fast enough to stop the transients destroying the fucking battery. It doesn't work. You need solid state. You need either an isolated DC-DC transformer or you need a diode that doesn't break. Now, lots of people said to me in comments, oh no, they did a simulation. It's impossible. Fuck off. Okay, look, as Sonny said in the courtroom, can we get real now? A simulator cannot map out the flow of electrons the way they did. Simulator cannot map out the inside of the lithium battery failure, okay? And I understand that simulations are very advanced, but they don't have the electrical gremlins that killed the innocent people on this flight, right? They've got amazing systems, but they are about, look at these things, they're freaking awesome. I would love to have a go. But look, these things are about simulation of flight and the incidents and how you handle them. It's not about electrical gremlins. And you can't, because no one will have foreseen what I have worked out here, as you will see. Here's a slew of clues. The bus power control units are powered by the two instrument buses. Okay, this is how they're able to be powered by the hot battery bus. Okay, so the bus power units are powered by the hot battery bus, but that's by two of the four airplane DC buses, which is the two centrals, which is the on-site and off-site, which is the two transformer rectifier units. Okay, there you go. Or the ground cart through the transformer rectifier units. Okay, all of this is saying that the bus power control units are powered by the critical DC buses. Simple as that. There's not 5 sources. There's 2 sources, the TRUs, and then it gets there from all these different parts. Okay, there's the transponder / line replaceable unit. It's called the ISS, Integrated Surveillance System. excuse me, 2100 by Rockwell Collins. A great unit. Takes 115 volts at 200 watts. There's two of them, left and right. There they are, left, right. 115 volts in on 2 RPDUs, 115 volts in on 2 RPDUs. There you go. So the transponder turned off over the runway threshold once load shedding dropped the remote distribution units, RPDUs, and all of their 150, not all of them, most of their non-critical 115 volt loads. These are not critical things. They would be if you're in the middle of the air surrounded by aircraft and you need air traffic avoidance, but as far as safety goes, when the aircraft needs to, it'll just kick it off, which is what it did. Now, the bus tie contactors and everything that works with the bus power control units. Notice here, in the left captain instrument bus, there is a tie contactor called the captain's instrument tie contactor. It is normally closed. On the right is the right bus power control unit, flight first officer instrument bus, and its bus tie contactor, normally open. So how does this work? When the bus power control unit is on and powered, it is holding that open with power. It keeps it open to keep these isolated. When this one is on, it's keeping that closed. Okay? Why? So that no matter what happens, if something fails, the left bus is kept up at any cost. So let's say we lose the left BPCU. This would close. Okay, that would be connected because this would see that that's off and it would be connected. Okay, so that's normally open, but if that is powered, it's key to keep it closed, which is going to push power through and bring that back from the dead. Okay, so that would have happened for a split second until the short circuit that happened here pushed its way through and then turned this off until the main battery relay opened. Now, the main battery relay you will see is normally open, controlled by the left BPCU as well. There you go. So after a certain amount of time, so when you shut down the aircraft, the main battery relay stays on for about 2 minutes. Okay? So therefore there is something which holds it shut. Sorry, which holds it shut and keeps it powered while the common core system is running and shutting down. In this case, whatever kept it shut lasted long enough to keep the short circuit connected for however long everything stayed offline. So when that turns off, when the left bus power control unit turned off, this one stayed on until it connected these together, and then you ended up with both instrument buses down until the main battery relay opened to get rid of the battery and bring current flowing normally, or voltage, whatever you want to call it, from the TRU back through the bus. There you go. That's the basic operating principle of the bus tie breakers. Okay. So now talking about what is the responsibility of these buses. We have the inner ones, which are battery backed, as you can see, via that logic. And then you have the outer buses, left and right. They are not battery backed. That's important. The non-battery backed is the ones on the left here, which are going to RPDUs, left and right. And then here are the two central critical buses that are battery backed. And you'll see that these have all of the critical things. The DC fuel pumps, now they're not 100% required because the fuel can flow gravity feed. That's completely fine. The igniters, so there's the left and the right igniters in each engine. You've got the left bus powered and the right bus powered, both stacked up. Okay, the igniters can also be powered by anything on that bus if that bus is up and running, which means when it managed to kick the battery off, the igniters did work because there was power coming from the TRUs, which were coming from the ram air turbine after the battery was isolated. Now, very importantly, notice that there's an entire valves bus on the less critical, on the RPDUs. That includes all of these valves, the Spar valve, the fuel management valve, and the PRSOV, high pressure shutoff valve. Okay, all of the valves are controlled on that, which is a separate bus. So that means the valve's getting its actual power through its relays from that, but the relays are being controlled by that, which means both of these have to work in perfect unison for everything to work fine. Why would they do this? Why would they put valves on a less critical thing? Well, the only time you need to turn the valves on is when you're on the ground. The only time you need to turn them off is if there's something wrong. Now, it's not the end of the world. Why would you want to turn the valves off when you're in the middle of flight? It's pretty much for a a fire. So therefore, there is a thing in the fire handles which allows electricity to come from any of the 4 buses to shut the Spar valve. Okay, and that's separate from this. That bypasses all of that. So that valve thing is separate for good reason. Notice everything else is on the critical battery-backed buses. If a pilot wanted to commit suicide, they'd simply pull the fire handle because there's no chance of restarting easily. Okay, not the fuel cutoff switches. Just get real. So what am I looking at here? How was the RAT able to deploy? The RAT's able to be deployed by either the main battery or the APU battery. And when I say deploy, I mean pull the trigger, which lets it out. Okay, so if the battery was stuffed, how did that happen? Well, it worked because the APU battery was still running, and it was able to take the information from the BPC, not the information, the loss of the buses from the BPCU. Hey, we're both off. And that tells the APU battery to connect the solenoid to deploy the RAT. Main battery was fucked. Okay, APU battery was still working and was able to deploy the ram air turbine as well as to start the auto start for the auxiliary power unit, which you saw happen towards the end of the incident. Okay, read all of that on the screen there. What's powered by it? Most importantly, the left common computing resource cabinet. Okay, only, and all the captains and first officers stuff. It's mostly about the left side. Okay, that's what typically runs. Okay, a remote data concentrator. This is important. People ask me, how did the remote data concentrator send the loss of the switch on position if there was no power? There are 2 sources of power for every remote data concentrator, and there are 2 channels for copper-fed data from the remote data concentrator to the switch, which turns it into fiber optics through that little port there. I'm a fiber technician. I was shocked to see the fiber optic connectors in this thing. There's like multiple fibers, and I saw a guy in a video cleaning it with a one-click connector. I just started laughing. Anyhow, I digress. So look, this thing takes 28 volts battery back bus and then 28 volts not battery back. So the outer, the primary is battery back. The secondary is the outer left, which is not. Okay. And then 2 switches to channel A goes to the left cabinet, channel B to right cabinet. Now the main here's another clue. The main landing gear truck, as we saw, was tilted as if it was in the retract position. When the reason this was able to happen, okay, without hydraulics and all the actuators working, is there's only one thing that is needed for the main landing gear truck position actuator to move, and that is a little spring inside the control valve is allowed to move, right, with very little electricity required. And once that spring opens up, it opens up the actuator, and hydraulic fluid is allowed to just simply flow as it wanted to, drain, okay? And then the gear changes position. That only happens if the landing gear lever was moved. So in this case, it was moved up. Nothing worked, but the only thing that happened was the landing gear truck tilt. Okay, read up on it, and you will learn. Okay. Now, critically important. The APU door opened. I'm just going to scroll forward a couple of slides. The APU door opened here, along with the APU inlet door, along with the APU auto start logic. That happened awfully late, didn't it? Why? Okay, the APU door would start to open as soon as the last remaining engine's RPM is low enough that its last, there's 2 VFSGs, and let's just imagine they're running at different speeds. Okay, imagine there was one which was managing to stay up and running well, and the other one was not. That's not how it works. They're both dying at the same rate. Okay, so basically the last engine's RPM is low enough that its VFSGs stop producing power and go offline. So it took a long time for that to happen, didn't it? It didn't start till here. Okay, that means the VFSGs were still putting out some kind of power to the transformer rectifier units, enough to create just a little bit of DC. Remember, we're talking about 235 volts AC going down to 28 volts DC. Okay, that's a big drop, which means current is in favor of the 28 volt. Okay, according to the preliminary report, that didn't happen, like I just said, until the 854 mark. This proves that the generators were still providing some power until this point. They were online until they were not. Note that the RAT also deploys when the generators are all offline at the same time, basically. Not identically, they're using a different trigger, but it's from the same thing. Power going from the TRU to the captain and first officer instrument bus. And that was precisely 13 seconds after the RAT actually deployed in this instance, or 7 seconds after it started supplying hydraulic power. So how does the APU start? First, it has to be armed. How does it start automatically in air? It has to be armed. So therefore, it's got to be in the air, and it has to have been getting some power from at least 2 VFSGs. Tick, that was satisfied. Okay. Then, if the bus power control unit goes, I'm offline, it doesn't send a request. It says, I'm offline, which says, you better do an auto start. Provided that, okay, the auto start function's armed, tick, that's done. Now, if there's 1 VFSG online, it'll wait 2 minutes. So we can take that off because this happened within 15 seconds. That's because no VFSG was online anymore at that timestamp. So auto start and the door opening occurs immediately with no delay. That happened there. Not back here. There. Okay? Now, the engine relight efforts. The thrust recovery sequence mentioned in the hopeless preliminary report does not talk about applying starter power to the starters because there was none. Okay? There was no fully functioning 235 volts AC available. The APU hadn't started yet. There was no ground cart in the air. The number 1 engine was still spinning fast enough that it was able to get a reversal of its inner core deceleration simply by igniting and applying fuel. How did it do that? Okay, look. The FADEX, which are independently powered by their permanent magnet alternators, completely isolated from the rest of the electrical system, right? Once the RAT had deployed and the battery was isolated, okay, the RAT was able to power the inner buses to power the ignition, and the fuel introduction was allowed to recommence. Okay, and so the number 1's core wasn't slow enough because it hadn't slowed down to a stop. Okay, it was able to windmill start and was able to reverse its deceleration and progress to recovery. Unfortunately, not fast enough. So during a windmilling start, now this is from a document, not from the preliminary report. This is now from a document showing how the windmilling start process works. The EC monitors the engine parameters and makes sure that it doesn't just throw fuel in. It gives the right amount of fuel to schedule, right, based on the best fuel schedule for all the things that are happening to ensure the shortest possible start time. And that's why this did so well to get as good as it did. Unfortunately, the second was not good enough. It was just too slow. Okay? The igniters would have both gone like crazy, inner and outer, left and right, as in the left bus and right bus would have both been powering all 4 igniters to try and get this working. Okay? Both igniters would have been on. Fuel entered at just the right amount to hurry up and bring this back. Not quite good enough. Okay? The RAT was deployed at this stage and was providing enough electricity to open the Spar valves, open the fuel valves, and to run the igniters, but it's just too late. Okay? So here's the timeline. I'm saying here the blue dot is exactly where they say the aircraft lifted off, when the air ground sensor switches to air mode. That's from the preliminary report. Then the ADS-B data said that 7 seconds from that was when the last ADS-B data was received. Okay, that's there. The photo we saw would have been somewhere in here. I've worked that out. I'm not going into that now. I don't have time. Here's where the left, as I showed you before, the bus tire contactors changed, and that's what brought down the second right bus. The RAT was spooling up, okay? And then it took this much time for something to happen where the battery finally isolated. Current was able to start powering here. Then the APU inlet door opens, okay? APU start process happens from the rear battery, and then 4 or 5 seconds later is when we see the beginning of that young lad's video of the plane crash. As horrible as it was. Now, if there was no DC short circuit, okay, if there was nothing wrong, and all they did was turned off the engines, okay, we wouldn't have seen the RAT deploy until about here. So there goes your suicidal pilot theory. And don't try and tell me, oh no, he committed suicide and tried to obfuscate it by manually deploying the RAM air turbine. No, just stop it. Just give it up. Okay? Just stop it. Stop your nonsense. The RAT deployed first due to the initial dual instrument bus failure. It's as simple as that. The short circuit meant that current could no longer flow from the rectifier units into the buses. Therefore, the Hall effect sensor current sensors registered that as nothing, and the RAT deployed immediately. Then things started to drop off because the battery was shorted and fuel relays started to behave erratically. Here's where my haters are going to be very upset. Very upset. Okay, I'm going to jump into a live diagram. This is the inside of a Spar valve. You can see how this works is once the Spar valve spins this way, it pushes that contactor, which opens it and says, stop turning. And the other way opens that contactor, stop turning. This had an issue. The reason I've got a photo of it is this had an issue in the early days, a manufacturing floor where these were getting stuck, but stuck in a safe way. Okay, it was just going to get stuck on. But it was enough that they had to redesign and remanufacture these things. So luckily, because of that, we got a photo of the internals of it. Okay, going out to a diagram showing the flow of electrons in a normal situation, even though in this case the battery is exposed to a broken battery diode. So here's a broken battery diode. Current is flowing into the battery. It shouldn't happen. So it's just constantly being exposed to this little 31 volts. And all of the transients, zaps, that are coming out of the C1 transformer rectifier unit are making their way into this through the closed battery relay, which is closed during flight, whether you like it or not. That's how it works. Okay, battery switches on. That's closed during flight. The reason for that is in case something turns off, the current immediately flows out of here to that without the need of something having to actuate. Okay, so normally current would flow out of the battery bus. Let's follow the blue line. Would go out to the fuel P300 cabinet left fuel control relay. Okay, I'm just talking about the left side here. Would go in through that, through the positive, would hold, either move or, let's say, apply current, apply voltage to the positive side, which would mean, yes, keep fuel open. So the Spar valve would have turned until it hit that little micro switch, and then nothing happens. No current flows. So this is just talking. So this situation is during flight. Okay, voltage going through there in the correct direction. Let's see the return path, green path, back to the fuel switch, through the run position, back to the current return network, back to the battery. Okay, everything's fine. At the same time, the remote data concentrator, I'm not sure if it's the thrust control module or the fuel control module. I believe it's just one for the whole thing. Okay, it's got like a 10 to 14 volt output running through these optocouplers or photocouplers, where the current flows through an LED and then through the switch to show that the switch is in that position. The light on the LED turns on, current is able to flow through this coupler here, and that current is inside this, and it says on, and sends that on position for that plus that, confirming to the left RDC, confirming to the right RDC, left and right RDC via the two different switches, and then via fiber optics, so that both the left, I shouldn't say RDC, sorry, left common core resource cabinet and right common core resource cabinet. So right goes through to the right, channel B, and left goes through channel left. And remember that this has two power sources. One is the battery-backed captain instrument bus. The other source of DC power is the non-battery-backed left outer bus. Okay? So here's the bus power control unit doing nothing. Okay? It's not doing anything at the moment with the bus tie contactors. Zoom out. All right. So here there's nothing happening with the fuel shutoff valves, the fuel Spar shutoff valves. There is another set of relays for the fuel high pressure shutoffs, and they're not involved in this at all. Not yet, anyhow. Okay, moving down. When there's a problem, what happened? Okay, battery has shorted. For a split second, this doesn't carry on for too long, for a split second while the main battery relay is still closed, before it has time to open, okay, the bus power control unit goes offline because there is no more current flowing to it. It's shorted. Okay, this one continues to work because it's not touching it. It's isolated. So what happens is it immediately shuts this to bring that back. Short circuit makes its way. Current all now flows backwards through here, through the battery, and to everything else. Not in the wrong direction, but has the capability of sending current in the wrong direction. Doesn't reverse, okay? It has the ability for current to travel in the reverse direction. How? We'll get to that in a minute, but just before you ask how's it possible, just try and understand what happens when current goes in the wrong, when power flows in the wrong direction. Let's look at the left circuit again. Before, I was showing the blue line leaving away. Now the blue line is coming towards the battery bus. Everything's in reverse. So now voltage, for some reason, which I'll explain in a minute, is going from the run switch around backwards through the diode and causing a reversal of the coil in the latching relay, a reversal of its action. The specification sheet for that says that the relay will not be damaged, but it may transfer. There you go. Okay, so it transferred in the wrong direction. Bam, snaps shut, sends the closed signal to the fuel spar valve, and the fuel spar valve shuts. Okay, that's how the fuel shut off, and that's why, okay, I haven't spoken about why the switch transition. Okay, the switch transitioning. Why? Well, current's trying to flow the other way now. It's going the wrong way. Well, it's shorted. It's not moving anymore. So therefore, this isn't going anywhere, which means the light turns off, which means this doesn't see it anymore. So the RDC is still online because it's powered by the non-battery back bus, and all it sees is the lack of a light. Its built-in failsafe does not need a confirmation, because what if the optocoupler had failed? So it takes enough information from the loss of the light in the right thing and the loss of the LED light in the right run and the left run, and it infers that as being, well, the fuel switch has changed position. So it logs that as a change of status and sends it to the RDCs and to the flight data recorder. Sorry, not to the RDCs, to the common core resource cabinets, computers, and then through the common data network to the flight data recorder. Now, look, you can sit here and analyze this a bit, and you'll understand, well, hang on, where did the reverse voltage come from? There were two possibilities. I had previously thought that perhaps the battery reversaled. I found the actual problem. Okay, so before we get to the problem, let me just talk about the relay. Thanks to one of my haters that told me I was an idiot and sent me the data sheet for the relay. Little did he know, he was giving me the ammunition that a guy like me needs to actually confirm my suspicion. Okay, relay will not be damaged by applying reverse voltage to the coil, although the relay may transfer. So here we can see it's giving you the time characteristics as per these military specifications. Here's the military specifications for the 28-volt version. This 14.5 means that they guarantee that the latching mechanism will at least function with worst case 14.5 volts. That doesn't mean that's the minimum. It means that they guarantee that with only 14.5 volts available, this relay will work. And that means it'll work in any direction. If you've got reverse polarity going on, it will work at 14.5 volts. Now, that doesn't mean that has to have 14.5. It might be down to 5. I don't know. There is also a negative 5 volt back EMF suppression, which means effectively like a diode, which stops voltage going in the wrong direction. But that's only up to a possibility of negative 5 volts and only on some models. I don't know what model this has, but 5 volts is not what we're talking about here. We're talking about a 28 volt battery where some of the current is choosing, look, electricity does not choose the path of least resistance. It chooses multiple paths. And even if it was only half of the battery power, 15 volts, that's probably enough to trigger this relay. Okay? Now, where did this power come from? Reverse voltage? How? Just look at this picture from this. Okay? This is not the Spar valve relay. This is the pressure valve shutoff relay. In the cockpit, okay, in the flight deck, there are capacitors on the 28 volt bus which are used to store energy required for shutting down the high pressure shutoff valves using capacitors, not batteries. Now that means they're on the positive voltage, okay? They're on, sorry, not positive voltage, they're on the battery back bus. The same bus which we're talking about somehow went backwards. Now, this might be very hard for people who don't understand how this works, but if you're an electrical engineer, come on, please think about this. Please think about it. Your capacitor's sitting there. All of a sudden, one side of it is shorted to ground. The electricity can either continue going through all of its circuitry, or it can take the quick, easy route, or both, a bit of each. In this case, at least a couple of volts, right, went back through the coil of, just pull this up, at least, I'm going to say roughly 5 to 15 volts, went back through this coil, made it activate in the wrong direction, okay, and then no other power was seen again because everything was shorted. That little bam was enough to flick this over to the wrong direction, and the magnetic latching action of these relays kept it in that position. It was all over, okay? So that power required came from these capacitors, which are on a circuit to the side, not under, not above, to the side, a different thing. And they went back out, jumped over the Spar fuel control relays in the P300, over their coils, and back to the battery, okay, in the wrong way. So this is just so out of scope of testing. So much so that even all of the engineers, yes, I'm not going to say your names, but everyone who's been talking about me like an idiot, no one could think of it. That's because nobody's thinking about DC electricity the way a DC electrical engineer does. Wow. There you go. That's what happened. Only 14.5 was absolutely required. It could have been less to activate the relay coil in reverse. All right. Now that you've got all of that, suicidal pilot should be the last theory, not the first. Okay? None of this needs to be said, as the rat could have only deployed before the engine's fuel cut off. I feel that people who kill or try to kill themselves along with others as a form of suicide and homicide generally want people to feel sorry, sad, and guilty for them. And they want it to be obvious that others failed to prevent it. Okay? They don't just quietly flick the switches off. Okay? I feel that murder-suicide is really meant to say, look what you've made me do, you'll never forget this, in anger. Okay? Like the seemingly never-ending school shootings we get in some countries. Okay, where the perpetrator wants their death plus the deaths of others, you know, to stand as evidence that others ignore their pain. Murder-suicides generally come from people who feel powerless. By orchestrating something really fucking terrible, they get some kind of control and make a statement. This was a respected airline pilot, not a baggage handler. No offense, baggage handlers. A mate of mine was a baggage handler as a kid. Come on, I'm not saying that. I'm just saying he didn't have any reason to feel like, you know, he was powerless and no one. Okay, I find it very, very hard to accept, and I did in the beginning, after the preliminary report and all of its nonsense, I found it very hard to accept that anyone would commit such a crime by quietly turning off the fuel switches at a stage of the flight that would probably result in the other pilot conducting a successful off-field landing and overpowering you. Okay, sorry, no. You would need 2 suicidal pilots, and you would, if you were doing that, you'd do it differently. Okay, this is not how people commit suicide. Sorry.